Welcome. In this class, let us begin by considering maximum work as well as lost work. When we are considering a process, we would like to know what is the maximum amount of work that can be expected from that process for various reasons. It could be for designing the process, or it could be for maybe evaluating the claims made by others toward the maximum work that is possible from a particular process. In the same vein, we would also like to know the amount of work that is lost. In other words, in comparison to the maximum work or the ideal work, what is the actual work that you are getting out of the system, and in the process how much work is being lost compared to the maximum work. To do that, let us start here. We have already seen that the change in entropy of the system plus the change in entropy of the surroundings is a positive quantity. Let us call that d epsilon way back in equation 1.6. We also said that the entropy of the universe can only increase. That was one of the statements of the second law. Now let us consider these surroundings as a heat sink, as it is called, at a constant temperature T0. This heat sink is a very useful concept. It actually refers to the bodies whose temperatures do not change despite the interactions with the systems that they are in contact with. For example, there are many things that can be considered as sinks or approximated as sinks. Some of them are given here. We can consider the Earth's atmosphere as a sink. It remains at a constant temperature for a certain period of time, or the Earth's surface could also be considered as a suitable sink, especially for biological systems of relevance. Let me also state this. It may not be completely clear right now, but it will become clear maybe after the 5th module or so. The heat sink is also supposed to be in a condition of internal equilibrium with no irreversible changes occurring inside it. Okay, this needs to be stated as one of the conditions of the heat sink. Let me state it again and leave it at that, and let us wait till the 5th chapter, 5th module, to make a little better sense of it. The heat sink is supposed to be at a condition of internal equilibrium with no irreversible changes occurring inside it. Under such conditions, if the system has a heat interaction of dq, a differential q, with its surroundings, which is the heat sink in this case, the entropy change of the surroundings can be written as, remember the second law that we looked at earlier, ds of the surroundings is nothing but minus dq by T0, minus because of the convention, the direction with which this negative is associated. Remember, we are writing this for the surroundings. So minus dq by T naught. Let us call this equation 252. Since we have already identified ds surroundings as minus dq by T naught, we will drop the subscripts now just for convenience, and ds will as usual correspond to the system. ds system plus ds surroundings, which has been replaced by minus dq by T naught, is the same equal to d epsilon. ds minus dq by T naught equals d epsilon. Let us call this equation 253. Remember, the d epsilon is the entropy that is created, and according to the second law, expanding universe and so on, it definitely needs to be positive. Therefore, the dq by T naught needs to be either less than or equal to ds. This directly follows from this equation, we are comparing this and this needs to be less than or equal to ds for this to be positive. We will call this equation 254. These are all very generic, coming right from the second law, and this equals ds for a reversible process that is undergone by the system and is less than ds for an irreversible process. Now, let us look at the first law, some very basics again. Equation 1.3, we know that dq, this is for a closed system, dq equals du plus dw. If we substitute the first law of thermodynamics in this equation 253, ds plus minus of dq by T naught equals d epsilon, we are in fact going to substitute for dq, we will get ds plus dq being replaced by du plus dw by T naught plus d epsilon. We have transposed the equation, therefore the negative sign goes away there. Or if we multiply throughout by T naught and then transpose the equation, we will get T naught ds equals du plus dw plus T naught d epsilon, and then grouping the terms appropriately we can write dw equals T naught ds minus du minus T naught d epsilon. We will call this equation 255. Now, note that d epsilon is positive, T naught is of course the temperature that needs to be positive in Kelvin. Therefore, the product of those two terms T naught d epsilon is positive, and thus dw needs to be less than T naught ds. Now, from here this needs to be positive and dw needs to be less than or equal to T naught ds minus du. Du we do not really know what is happening there. We will call that equation 256. Now, if we integrate this expression, let us say between the states of 1 and 2, it is straightforward integration, integral dw is w, this remains, this inequality remains less than or equal to T naught ds between integrated between 1 and 2 gives you S2 minus S1 minus du integrated between 1 and 2 gives you U2 minus U1. We will call that equation 257. Now, note this equation, this is some quantity and this is some quantity, and the maximum work possible, since w is less than this, the right hand side, less than or equal to the right hand side, the maximum work that is possible is when w equals the right hand side, and therefore the maximum work possible, which happens to be under reversible conditions, if indicated by w max, can be written as T naught S2 minus S1 minus U2 minus U1. Therefore, we have a measure of the maximum work that is available from a process in terms of the state variables of the system. T naught is of course the temperature of the surroundings, S2, S1, U2, U1 all correspond to the state variables of the system. Let us call that equation 258. We started out by saying this, let me complete this part by re-emphasizing this. The maximum work can be used to arrive at limiting conditions, for example, the maximum possible work for a closed system, which can in turn be used for quick estimates, to evaluate claims on design, as well as to begin with the design itself. The lost work, as we said, is the difference between the maximum work and the actual work. Therefore, the ideal or the reversible work minus the actual work. The reversible work, we have an expression here T naught ds minus du that we got from earlier. The actual work happens to be T naught ds minus du minus T naught d epsilon. Therefore, these two terms cancel, these two terms cancel. We have an expression for the lost work as T naught times epsilon. This is integrated. After integration, we get work lost equals T naught times epsilon in terms of the sink temperature, the surroundings temperature assumed to be constant, times the entropy that is created. We will call this equation 259. See you in the next class.